currently working in the autonomous insect robotics lab. So the work let me talk a little bit about the fellowship first. So I'm a recipient of this year's Herbal Fellowship. It's with a focus on data science and try to showcase how you can, in different realms of research, how you can use data to explore any kind of aspects. So since I'm working in robotics, I'll be talking about how do I use data to kind of lead to my control design, architectures, building, and what do I know from the data / like what's the future work. So this is a little. So today I'll be giving my talk mostly just around my project, which is what I called it. The name of the robot is called the DirectHop. It's pretty intuitive. It's a
controls. Be sharp.
Give me 1 second, guys. It's not really showing later.
Can you leave with the controls on? It's fine. We don't know how to, let's try this.
Well, I think it's just showing it's recorded.
Okay.
It's not an issue.
Randomize from here. Try now. Then go away. Is that
clickable? Oh, it might be just click OK. I think it just was spray once.
Sorry about that. Would you have to go over the control?
And I don't think it's going to cover any of the slides, so we should be good. So let me just start over. I'll be presenting DirectHop. It's a direct drive robot that can both control the jump height and self-right. So what I'm proposing is a self-ground direct drive robot that mainly tackles the two problems in insect-sized robotics, especially in locomotion. Like in the title, I'm trying to figure out how to do autonomous self-riding as well as to do jump height control. So sort of the motivation, it's most of the microrobotics platform that exists today. They can't really control jump height other than it's a one single shot device. But what we are trying to propose is we can have a direct drive which provides the opportunity to do control jump with navigating the goals of minimum surmounting a 17-centimeter staircase, as you can see in an urban setting. So I guess it's covering the title, huh? I mean, I can't really access the Zoom screen. That's fine. I'll just talk about it. This might sound stupid, but so the title, it's the biological history of jumping. So there's sort of two, I'll call it fields in terms of jumping actuation type. The first one, it's called the spring-loaded, and from a biological standpoint, you can often find this sort of actuation type in a flea. About this actuation type, it uses store and release actuation type. So how it works, you have a spring, some sort of elastic element, then you store the energy into it, and with the help of any biological latches or gears, then you're able to release the entire energy stored. So this comes with doing maximum peak height, so you could jump as high as you want as long as you can store enough energy. But this also comes with a drawback. It's called all or none, which means you release that jump, you can't really do anything about it. The other actuation type, it's what we're proposing, and then you use it from, it's called the direct muscle. Illustrated by the figure, you can see if, like our human being, if we jump to a targeted position, we're able to just use neural feedbacks and do whatever sensor control to achieve it. So this actuation, it's called direct actuation. It could do variable height, and like I mentioned, it could do targeted distance achieving. And we're able to get a closed loop as clarity. So I'll be talking about how to design the entire closed loop. So our background, it's most of the engineering platforms existing, they often mimic the design of a fleet. But what we're trying to do is we're trying to build a robot that we think about control first, and then we see if we can use any algorithms to detect the precise jump height and to concur in urban settings. So some of our motivation, it's our number one motivation is to do indoor navigation. So like I mentioned, our robot to be able to clear like a standard 17 centimeter stair height. This is any sort of urban settings. So like you see from Boston Dynamics, all those like robot, they're able to climb up the stairs. So we're trying to see if our system can happen to do the same. The second motivation is we can do a low cost deployment. So our hopper, the entire manufacturing cost, it's under $5. So comparing to robotic stocks or whatnot, it's considerably pretty cheap than that. And we have the huge potential to deploy multiple of the hopper into the real field and then do like a swarm application. We're also trying to see if we can deploy this into unstructural terrain. So this requires predictable jump, which direct actuation offers. Also to do variable jump height control to navigate like super complex environments. And this also has the potential to do search and rescue. And this one, it's has been going on in the lab for a while. It's one of the motivations in my lab. It's to do space exploration. Part of the reason why it's in space, the performance scales pretty nice with low gravity applications. So what we're developing, it's like sub-grand robots will have a huge potential in space. So I'll be talking about how we decided to design and fabricate the entire direct drive architecture. So here's kind of a system breakdown of the system. On the left, it's exploded view of all the parts. So our system is relatively simple. It has a foot, which lies on the bottom, and the source linkage, it's the one that you can see that kind of acts like a linkage bit. So the linkage has what I separated to be a bottom plate, a top plate, as well as flexure hinges. So those are the main components. I'll go into detail in the next slide. And our actuation type, it's mostly driven by a coreless DC motor. This DC motor, it's 220 milligrams. And a little background about motor, it's we choose coreless because it doesn't really have any rotational inertia. So think about if you have to jump super fast, your jump is almost instantaneous. So without the rotational inertia, then you're able to achieve that rather than having a gear motor. Um, so to talk about more about how the system actually works, I characterize the entire jump sequence into two phases. The first phase, it's the launch phase. So it utilizes the launch string. I don't know if you guys can see my mouse. So it utilizes the launch string, which so at the very beginning, the motor will be set towards the foot, and by spooling the motor, we're able to compress the launch string, which will just draw the entire linkages upward for the jump. And here's kind of like a sequence view of where it's the motor in terms of from the beginning phase to the last. And on the bottom, it's mostly just showcasing how we like coiled up the string onto the shaft and in order to do the jump and the retract. And phase two, so you can see after the motor gets up to the top, it will stay there. And so it's sort of like the CAD shown here, the motor will be all the way on the top. And the reason why it's not sagging down, it's because the launch the launch string it's attached to the shaft now. So it's kind of like affixed on to the top. And in order to track the motor back to its feet, we introduce a retraction string illustrated here. So how it works, it applies a bidirectional control onto the motor, and just in plain word, it's to spool the motor in an opposite direction in order to pull the motor backwards. Something to take away about source linkage, it has the functionality that constrain the entire motion to be purely 1 degree of freedom. And the reason why we are considering this is to ensure any rotational output from the motor translates purely into a translation of vertical forces. And then we don't want any parasitic torques. So I'll be talking about how do we actually fabricate the source linkage as well as the entire system. So what we are using is how do we actually build a system that's rigid but also flexible at such a small scale. So there has been studying going on, which we utilize a method called smart composite microstructures, also known as SCM processes. So how this works, it's we have 11 layers of different stack. We uses like 122 micron carbon fiber sheets. So you can see from the right figure, we have 4 of them just for structural rigidity. And in order to bond everything together, we use the 13 micron polyamide. This is acting sort of like an adhesion. So just to bond the carbon fiber with each other. And in terms of the flexure hinges, we're using, for the bonding, we're using the FR 1500 adhesion, but with the flexible hinges, we're using the polyamide. And the right figure here, it's kind of just showcasing what's the layout of each layer, and then on the section view, this shows after the heat press, it's able to have the view, and then I'll be. So this slide, so you might wonder how do we cut that sort of stuff, like what sort of fabrication method we used. We used a pretty pulsatile laser with a diode diameter of 10 micron. And this is by frequency driven with a diode wavelength of 355 nanometers, just to just to increase the precision. Sorry, give me 1 sec. So how it works, it's we can load the XI file into the system, and then it's able to cut the cut path. And this is just a illustrative of how we're able to produce anything in the fast turnaround time. And with the coin next to it, you can see the relative size. And just to showcase more about how the linkage is able to translate anything into a purely 1 degree of freedom motion, here's a slow mode video of me using a tweezer, and you can see the bottom plate, it's fixed to the tweezer, and I use a tweezer to like pull the linkage upward. Then you can see the entire motion, it's pretty much just doing a vertical force. And then once you let go, there's some hinge stiffness is able to pull the entire linkage back down. So in terms of, so how do we actually deal with actuation type? In terms of motor control, there's two big areas. One, it's voltage control. The other one, it's current control. So I'll be given the comparison among each other, and then why did we choose current control? So let's start with voltage control. For voltage control, it's simple to do since it doesn't really need any feedback system. You just connect the terminals of the motor, feed it any sort of given spec voltage, then the motor it's able to run. But one question about that, it's voltage control, it's pretty vulnerable to changes in any attachment wires. And especially in microrobotics, the wires snaps all the time, so we have to replace it super often. This is one of the drawback that we can't really do voltage. In comparison, the current control provides a pretty good alternative. It's that the current control actively rejects any serial resistance, which in another word, it's if we change the tether wires, it won't not affect the control algorithms at all. The second reason about voltage control, it doesn't really do a good job for dynamic lag as the motor spins up. So what this really means, it's when we feed more voltage into the motor will tend to speed crank faster. So there will be a sort of lag introduced, and then those lag is pretty hard to overcome. On the other hand, for current control, it's able to dynamically adapt any voltage we give into the system and then be able to just set into a current set point. For voltage control, voltage it's voltage it's proportional to the angular speed. And then like I mentioned, once the motor speeds up, there will be a lag. So this will introduce to an unpredictable force. Whereas the current control, by design, motor, it's able, so the motor torque, which is generated by spinning the motor, it's equal to just the motor constant times current. So you can see if we have a set point current, we're able to get what the torque it's operating at. So with the opportunity to do current control, we're able to make sure if we have operating at a set point current, we're able to see if how many torque is applying and how does that related to the height. So this slide I'll talk about how do we put everything together in terms of control architecture. So in terms of coreless motor, inductive delay inherently in the motor, it's a major issue since the launch is almost instantaneous. So in order to go about this, we introduced a dual path architecture. As you can see, there's a path on the top, which is the feed forward, and then there's the entire closed loop on the bottom. So the feed forward path, it computes a baseline duty cycle. So duty cycle, it's like the percentage that we're operating the base voltage at. So the feed forward works as like a sudden jump onto like basically overcome the inductive delay in the motor just to get to the set point as fast as possible. And the feedback PI controller, this basically corrects any back EMF happen in a motor. So when the motor cranks up, other than the power that you feed the voltage into it, there will be like an internal spinning. So that'll create what's so-called a back EMF. So this the feedback PI controller corrects for that, as well as any dynamical error in the system. We also introduced a digital low pass filter. So the reason we are introducing the filter is to condition the raw 40,000 hertz sensor data that we're operating at. So the controller doesn't really get confused with if I should chase for a high frequency noise. So I'll give a little bit more background into the digital low pass filter that we're using. So we're using a filter called the exponential moving average. So here's the equation for how it works. We wanted to get the current filtered output. It's often times depending on the loop frequency that we're collecting the data. This depending on X, which is the noisy sensor reading, and the 40,000, it's just the loop frequency that we're turning at. And we also just to use the previous filtered output. And alpha, it's basically the smoothing factor of this. We from testing, we decided to go with 0.1 just to have a fast enough, and then we're pretty much seeing the clean data from the noisy sensor reading, but alpha at some parameters that you're able to tune. So one thing about, you might wonder why we use this filter other than common filter or other low pass filter. It's because the PMA filter doesn't really, so from the equation you can see it doesn't need to store any past numbers of X and only use the values of Y that we have. So this is exceptionally good in terms of deploying onto a microcontroller, since it's more memory and computational effective. So by introducing the low pass filter, we're able to extract the current state from the noisy sensor data, and we also be able to just prevent the feedback PI controller from chasing any transients. So here I'll be given, so here's a current response plot that from a representative experiment. So one thing to notice, it's from a current response, we're able to see, we're interested in seeing the rise time, the overshoot, and the steady state behavior. So the rise time, we're able to see about 20 milliseconds. This is almost instantaneous output, which, like I mentioned before, for a more trying to like mimic the biological jumping, we want the rise time to be as fast as possible. So 20 milliseconds, it's almost instantaneous, but this is one of the future works that I'm currently working on. In terms of the overshoot, we're seeing less than 20%. The reason why we care about overshoot, it's we're applying 8 volts to operate at, to give a little bit overhead in terms of control, but this does come with the drawback of we could potentially burn out the motor. So we want to check the overshoot to be within a reasonable amount in order to not blowing out the motor. And we also check the steady state behavior. So you can see from the colored boxes, our steady state remains pretty stable within 5% of the air. So with all the background information, how do we turn our algorithm into a predictable jump? So here's the statistical validation that we did. In order to characterize the jump, we operate the system at 3 different current set points. We operated at 0.15, 0.25, and 0.35 amps, and we ran 5 experiments for each and reported the experimental mean plus or minus 1 standard deviation. We're able to have a highly linear relationship with R square of 0.98, which validating if the robot sees, like, for instance, if the robot sees a 150 millimeters there with this relationship, it knows how much current to pull. So this gives the potential to plan and execute specific jump heights. So how do we use the validation to actually test if the robot is able to summon a 17 centimeters stair height? So here's a vertical jump. You can see the hopper is able to achieve a 256 millimeters center of mass height. So center of mass is defined by where the motor position is, since the motor takes up about 80% of the overall weight. And we also want to be careful in terms of the entire hopper is able to achieve be able to surmount the 17 centimeters height. So we were also interested in seeing what's the foot clearance height. So this figure shows the foot clearance height is about 228, which you can see both of the height achieved. It's way above the 170 millimeters height. And we're also interested in, since we did everything in terms of vertical jumping, but in order to go up to a stairs, you need some sort of forward motion. So I 3D printed a 45-degree angle plate. That's the blue-ish thingy over there. And then we just place the motor, we just place the hopper on top of it and then see if it can get up to the 1700-meter stair height. So I also characterize this with 5 jumps. It has an 100% success rate, but that does depending on where I place the angle plate. But we proved this is viable. So the next step will be introducing some feet onto the hopper and then be able to provide forward motion. So this gave us confidence in terms of the algorithm. It's able to let the hopper to conquer any human scale obstacles. And this really just gives us potential to do any real world setting deployment. So I talk about the source linkage actuation 1 degree of freedom motion, but in order to do multiple jump, we need the robot to be able to self-right. So since the landing is pretty unpredictable, how do we make sure the robot will get back to the feet and then be able to jump again? We decided to use a tortoise-inspired carbon fiber roll cage, which is entailed by the black. Let me get a laser. By this, so the tortoise-inspired roll cage has an aspect ratio that, as long as the height to width ratio is about 0.9, this could maximize the monostatic stability, which this also comes with when the center of mass is below the center of curvature of the cage, the hopper is always able to passive self-right. And the sub-figure B over there, it's to introduce, so the thin black line, it's showcasing a top view of the cage. So by introducing the cage, we introduce 4 quasi-stable point, which showcasing by the star. But you might wonder what's the system gonna behave after the jump. So like I mentioned, the source linkage, it's only doing 1 degree of the motion. So after the pass jump, the functional center of mass, which is the motor, will be above the center of curvature, and this violates the right condition, which it's your center of mass has to be below the center of curvature. And you can see on figure B, the hopper after landing might land into one of the 4 quasi-stable point. So after integrating the passive self-cage, the system will inherently kind of falls into one of the 4 stable points. So how do we actually get it out of the stable and then back to its feet? That's the motivation for doing process called dynamic perturbation, which is also an active center of mass shift. So here's a montage of the self-righting process. So you can see starting at frame 0, the robot lands on one of the 4 quasi-stable point with the motor extended above the center of curvature. So what happened is we can reverse the polarity, since the bidirectional control of the motor that we can do, we split the motor in a counterclockwise fashion, and that pulls the motor back to its feet, as you can see from the second frame here. And this active center of mass shift, by just pulling the motor back to its feet, this introduced an airborne phase, which happening from the 0.52 seconds frame onward. And the reason why for this, it's in order for passive self-righting, we want the center of mass to be below the center of curvature. And this introduced a dynamic kick, which this sudden acceleration by pulling the motor back to its feet, it's able to generate enough momentum transfer that have enough energy to kick the robot out of the phase. So before I play this video will showcase 4 consecutive jumps. So this involves doing the launch, landing, and then doing what we talk about in terms of the self-righting with the use of passive roll cage design, as well as an active perturbation we did. We're seeing a 90% success rate, and this system jumps for 4 times before the wires start tangling, and that could just affect the performance of the hopper. So you can see the landing behavior, it's super unpredictable. That's one of the considerations that we have in terms of doing the active shifting, just to make sure you have enough energy to kick it out of the stable point. So now we see the system works in terms of jump height, modulation, and self-righting. How does our system actually perform in terms of energy-wise? So I'll be talking about in microrobotics, I'll be talking about mass-specific power density, as well as electromechanical efficiency and cost of transport. So our system is able to achieve a 233 watts per kilograms over a 15 milliseconds launch window. This number might seem a little odd, but just to give you guys some more context behind it, it's for this number, it's almost double the limit of the biological muscle. So this kind of proves the point that we don't need any elastic storage element. We're able to achieve 40% efficiency. For a sub-gram motor, this is exceptionally high. We have a hunch that the reason why it's so high is because we have an optimized impedance matching, which we basically operate at near the peak efficiency when the motor is pulling near 45,000 RPM. For the cost of transport, we're able to get 16 joules per kilograms per meter. And for comparison, in our lab, the RoboFly, it's a micro flyer. It has like the 16 joules per kilogram per meter. It's almost 2 orders off than the cost of transport for the fly. This proves the next step in terms of onboard control, and here's the source. It's almost 2 orders lower than the cost of transport for the RoboFly, and this just gave us confidence in terms of moving everything on board. So this slide I'll be talking about comparing my platform to other existing platform. So I kind of just considered in terms of the platform masses, the jump height, but most importantly, I want to discuss the options to do high modulation and self-righting. So you can see comparing like the same mass aspects, the SNU fleet, it weighs about the same of 1.1 grams. Well, it can jump higher, but it doesn't have the ability to do high modulation or self-righting. Whereas the hybrid hopper, it's less weight, but it can do high modulation, but not self-righting. So what we have, it's DirectHop, it's the only near subgram platform that's able to do both high modulation and self-righting. And this is really the minimum requirement if you want to do any significant exploration on like any unstructured environment. And just to emphasize the main point of doing controllable jump height, it's often a time you don't really need to jump pretty high as long as you can do the jump you want. So we're trying to prioritize jump control other than to achieve just the peak height. So anything right now happen in a lab setting, how do we really make it to be untethered autonomy? So we'll move to onboard control. We'll just introduce any electrical components into an onboard flexible PCB. So some of the components I'll be integrating, it's the microcontroller unit. This is sort of the brain of the entire system. So it will operate all the control architectures. And the H-bridge is the one that provides the functionality to do bidirectional control, which is why we have the option to do split the motor in one direction, and then we can just counter split in another direction. Then there's an inertial measurement unit. Since if we do an untethered operation, we would like to know where the robot's at comparing to its local frame. The IMU has the ability to give that information. And the current sensor, it's the one that modulates the current and then be able to close the feedback loop to operate at the set point that the robot has to do in order to surmount any obstacles. In terms of energy harvesting, we could use, so microrobots has a benefits of a high surface area to volume ratio. So we could either use a 330 milligrams LiPo battery. This could power more than 1,000 jumps by one single discharge. Or we can use 10 milligrams solar cell with the help of some 100 microfarad capacitors to store enough energy. And ideally with a direct sunlight application, this could power 1 jump per second. So to summarize, our hopper demonstrate by combining mechanical design with data-driven architecture, we're able to unlock the high controllability as well as to achieve any desired deployment in a real-world setting. And here's the reference that I used throughout the presentation. And thank you guys for your time, and then I'll take any questions.